Hello and welcome back to Chapter 2. Today we're going to look at Part 1 of Section 2.6 that deals with rational functions. Before we begin, let's identify what a rational function is. A rational function is a function, and in this case we're going to call it f of x, that is equal to a polynomial, which is represented by the function n of x, divided by another polynomial, which is represented by the d of x. Now, n of x is a polynomial, d of x is a polynomial. Remember that our d of x, though, cannot equal 0. Okay, the domain for this rational function will be all real numbers except values that are going to make your denominator equal to 0. So, I guess if you want to think of this in a short and simple way, a rational function is just a fraction of polynomials. So for example 1, we want to find the domain of the function f of x equals 3x divided by the quantity of x minus 1, and then we want to discuss the behavior of the function near any of your excluded values. And our excluded values are essentially the ones that are going to be the zeros of your denominator. So, to look at our domain, the first thing we're going to do is we're going to find which values for x is going to set that denominator equal to 0. So when we solve this, we find that x is equal to 1. So our domain then is going to be all real numbers except x is not equal to 1. Now if you go in and sketch this graph, you'll see that you end up getting, and this is going to be at a value of 1, a graph that goes something like this and something like this. So when we look at our end behavior of our function near our excluded values, or the value of x equals 1, so I'm just going to come in here and draw, the blue line represents the x equals 1 line, and if we look at our function as we're coming in from the left, so in other words, as my function gets closer and closer to 1 from the left, and I'm going to show that as x is approaching 1, and then I'm going to do the minus like that as an exponent, and this means as x is approaching 1 from the left. The negative sign here means from the left, and as x is approaching 1, we're going to come in this way. Our function f of x is going to approach a negative infinity. In other words, our graph is going to go and it's going to continue to decrease to negative infinity. Now I'm going to do the same thing, except I'm going to look at the opposite side of my graph. So now I'm going to look at x as it's approaching 1 from the right, and we're going to look at our f of x values, which are really our y values. And as I come in from the right-hand side, denoted by the plus sign here, I see that our graph is approaching a positive infinity. So we're going to say f of x approaches a positive infinity. So in your book, you'll see that you have this notation right here, that f of x is approaching a negative infinity as x approaches a negative, 1 from the left, and f of x, or your y values, are approaching a positive infinity as x is approaching 1 from the right. Now with that being said, we have kind of similar type of rules when we're looking at horizontal and vertical asymptotes. The first one says the line of x equals a is a vertical asymptote of the graph of f if your y values approach either a positive or negative infinity. So if you go back and look at example 1, you'll see that our x and y values were approaching, in the last case they were actually approaching a positive and a negative infinity. Then the second thing we have to look at, the line y equals b is a horizontal asymptote of the graph if you have your function approaching some number, and in this case b, as your x values are approaching a positive or a negative infinity. And we'll take a look at this in another example. So if we just look at a few quick examples, this function here is the function of 2x plus 1 divided by x plus 1. You'll see as we approach, in this case we have a negative 1, so as we approach negative 1 from the left, my y values are going to increase without bound. And as we approach negative 1 from the right, our y values are going to decrease without bound or approaching negative infinity. And because we're approaching a negative infinity, as our x values are approaching this vertical asymptote, that tells us that we have a vertical asymptote. Now, on the other side of things, if my y values are approaching a certain number, and in this case, if you notice, as my x values go closer and closer to infinity, my y values are going to get closer and closer to this kind of imaginary line or this asymptote here. Likewise, if I come in from this direction, this tells me I have a horizontal asymptote. Okay, in this type of a graph, which we will study when you have kind of a curve in this corner and a curve in the opposite corner, and it could be in the opposite two corners, this is what we call a hyperbola. And we will be dealing with these later on. I think it's actually second semester. Let's go ahead and look at our middle graph here. Now, as your x values approach either a positive infinity or a negative infinity, you'll see that our graph is actually going to get closer and closer to the y equals 0 line. What that tells us then is that we have a horizontal asymptote. Now, my y values are not going to increase or decrease without bound. Our y values are actually going to kind of flow here. So I don't have any vertical asymptotes, but I do have a horizontal asymptote right here. And if we look at graph C, you'll see that as our x values approach 1 from the left, our y values are going to increase without bound. And as our x values approach 1 from the right, our y values also increase without bound. So because we're approaching infinity from both sides, this tells me I have a vertical asymptote. So let's look at some general rules to tell whether or not we have vertical or horizontal asymptotes. If we're given a polynomial function, or a rational function, so we're going to see that n of x divided by d of x again, and n of x and d of x have no common factors. In other words, we can't factor anything out and cancel common factors. They're in their simplified form. Then we say that the graph has vertical asymptotes at the 0 of the denominators. So to find vertical asymptotes, we're going to take our denominator here and set it equal to 0 and solve. To determine if we have horizontal asymptotes, we're going to look at a couple different things. Because with horizontal asymptotes, we're either going to have one horizontal asymptote or there will be none. Okay, and the reason or the way that we determine that is by looking at our polynomial functions in both the numerator and the denominator. Now, if the degree of the numerator is greater or less than the degree of the denominator, then we say that our graph has a horizontal asymptote that's equal to the line of y equals 0. And an example of this would be something like, we'll say y equals 3x squared divided by like an x cubed function. It could be x cubed plus 1. It doesn't matter. All we're looking at is the degrees of the numerator and denominator. Now for part B, it says if the degree of the numerator equals the degree of the denominator, then the graph has a horizontal asymptote at the line y equals your coefficients of your numerator divided by the coefficients of the denominator. So again, if we have y equals, and let's just say we have 3x squared plus 1 divided by 2x squared minus 6, I'm going to look at the degrees because those are the same. Then I'm going to take the ratio of my coefficients. So my horizontal asymptote will be y equals 3/2. And our third scenario says that if the degree of the numerator is greater than the degree of the denominator, then we have no horizontal asymptotes. So if we had y equals 3x cubed plus 1 divided by x squared minus 7, because x cubed is greater than x squared, we would say that there is no horizontal asymptote with this graph. So example 2 wants us to find the horizontal and vertical asymptotes of the function f of x equals 5x squared minus, or divided by x squared minus 1. So the first thing we're going to do is we're going to look at our vertical asymptotes. Vertical asymptotes come from the denominator. So I'm going to take that x squared minus 1, set it equal to 0, and that's actually a factorable function. So that's going to give me x minus 1 times x plus 1 equals 0, which tells me that x equals a plus or minus 1. So these are going to be my vertical asymptotes at x equals plus or minus 1. Then I'm going to look at my horizontal asymptote. To find out if I have a horizontal asymptote, I'm going to look at the degree of the denominator and the numerator. Well, in this case, both the degree of the numerator and denominator are the same, so I'm going to take a ratio of their coefficients. So I have y equals 5 divided by 1, which is 5. So this right here then implies that I have a horizontal asymptote at y equals 5. And if you remember, when we draw these on our graph, we're going to draw horizontal and vertical asymptotes as dashed lines. It's not part of the graph, but it just shows that we actually have a graph that is approaching but that will not cross those asymptotes. So with that being said, we have some guidelines for graphing rational functions. And the first thing you want to do is you want to simplify your function if possible. In other words, if you have factors that you can factor out, do that up front. Once you've got a simplified equation, then you're going to find and plot your y-intercepts by evaluating f of 0. Then we're going to find the zeros of your numerator, and remember the zeros of the numerator are really going to be your x-intercepts. So you can plot your y-intercepts, then you can plot your x-intercepts. Then we're going to find zeros of the denominator and sketch those in as our dashed lines because those are our vertical asymptotes. Then we're going to find and sketch in any horizontal asymptotes. And then what I would like for you to do is I'd like you to plot 1 point between and 1 point beyond each x-intercept and vertical asymptote. And I'll show you how to do this. We're going to create a table. Then we're going to use some smooth curved lines to complete the graph. And then we should be all done. Now the one thing I did want to make a note of is I want you to put your zeros of the numerator and the denominator in increasing order from smallest to largest so that we can create those test intervals which we did a couple sections back. So for example 3, we're going to sketch g of x equals 1 divided by x plus 3 and state the domain. So if we go ahead and we figure out let's do our y-intercepts. Y-intercepts are found by setting x equal to 0. So we end up with y equals 1 divided by 0 plus 3, which is equal to 1/3. So that gives me the point 0, 1/3 to graph. Then I'm going to find my x-intercepts by taking my numerator and setting that equal to 0. So I end up with 1 equals 0. And because this is not true, this tells me that I have no x-intercepts. Then I'm going to look at vertical asymptotes. And vertical asymptotes come from the denominator. So if we set our denominator equal to 0, we're going to calculate our vertical asymptotes. And I find out that I have a vertical asymptote at x equals a -3. Then I have to look at my horizontal asymptotes. And to do that, I need to look at the degree of the numerator. Well, the degree of my numerator is 0, because that's x to the 0 power, divided by x to the 1st. And because the degree of the numerator is less than the degree of the denominator, this tells me that I have a horizontal asymptote at y equals 0. Now I'm going to take my vertical asymptotes and x-intercepts and put them in order of increasing numerical values. And in this case, since I've only got the x equals -3, I've really only got 2 test intervals to look at. Okay, so my test interval, and I'm just going to put ti for my test interval. I'm going to look at the values from -infinity to -3 and -3 to a positive infinity. Then I'm going to find a value, so I'm just going to put value that I'm going to arbitrarily pick that's within this test interval right here. So I will pick a -4 and 0. Then I'm going to evaluate the function at that point. So I have f of x equals, well, if I plug a negative 4 in, I end up with negative 1. And if I plug a 0 in, I end up with 1/3. Then I notice the sign difference. I notice that I had a negative sign here and a positive sign here. So then I'm going to graph a point. So this will be our point, and I have the point -4, 1, and 0, 1/3. So now I'm going to take this table and I'm going to graph, and I'm just going to sketch this out. So now I'm going to sketch in what I know. I know that I had a vertical asymptote at x equals a -3. So I'm going to come in and sketch my vertical asymptote. I also know that I had a y-intercept at 0, 1/3. So I can go ahead and plot that right here. Then I'm going to pick the points that I've selected. And I have the point -4, and this up here should be a -1 as well. So -4, -1 is going to give me a point right here. Then I also have the point 0, 1/3, which I've already got. I know that I had a horizontal asymptote at y equals 0. So now, and you can use your calculator to help kind of guide you, but you're going to end up with a graph that looks something like this and this that goes through that point there. And this would be your completed graph. Next, I'm going to sketch f of x equals 2x minus 1 divided by x, and then I'm going to state the domain. So I'm going to go through the whole gamut where I have my y-intercept, and I find this by substituting 0 in for x, and that's going to give me nothing, because if I plug a 0 in for my denominator, I'm going to get an undefined function. So I'm going to say none. My x-intercept I get from my numerator, setting that equal to 0. So I have 2x minus 1 equals 0, which tells me that 2x equals a positive 1, and x then is equal to 1/2. So this is my x-intercept. I have a vertical asymptote when x equals 0, and a horizontal asymptote. I have, looks like a first degree in the numerator and a first degree in the second, or the denominator. So that's going to give me the ratio of my coefficients, or the fact that I have y equals 2. So now I'm going to create a table that has test intervals using my x-intercepts and my vertical asymptote. So I have 1/2 and 0. So our table then is going to look like this right here. Now my test intervals are going to go from a -infinity to 0. I have from 0 to 1/2, and then from 1/2 to a positive infinity. And remember, 0 and 1/2 were my vertical asymptotes and x-intercepts. Then I'm going to go ahead and pick some x value. So, and we can even say x value. Now between 0 and a negative infinity, I'm going to select -1. Between 0 and 1/2, I'm going to pick 1/4. And between 1/2 and infinity, I'm going to select 1. So then I'm going to have to evaluate my function f of x at those x values. And if I plug a -1 in, I end up with a 3. If I plug a positive 1/4 in, I end up with a -2. And if I plug in a 1, I also end up with 1. Next, I'm going to look at the sign of my function. And I see that I have a positive, a negative, and a positive. And then the last thing I'm going to do is I'm going to create my points that I'm going to plot. And I get that from my -1, 3, my 1/4, and -2, and 1, 1. And now I'm all set to sketch. So if I go down here and I sketch the coordinate plane, and I'm going to go ahead and start out with my vertical asymptote. And remember, your vertical asymptote was at x equals 0, which is really the y-axis. Then we had a horizontal asymptote at y equals 2. So I'm going to come up here through y equals 2. And I'm going to plot my test points at -1, 3, 1/4, -2, and 1, 1, which is right here. So then, again, you can use your calculator to guide you, but I know that if I have a graph that looks like this, we're not crossing our horizontal and vertical asymptotes, so we're going to end up with something like that, and something that ends up like that, which is a hyperbola. Next, we want to look at f of x equals x divided by x squared minus x minus 2. So we're going to go through the same process. We have a y-intercept. I'm going to plug 0 in, and I get 0 divided by a -2, which is y equals 0. I have an x-intercept at the zeros of my numerator, which are 0, 0. So when x equals 0, then I have my vertical asymptotes. And I'm going to get my vertical asymptotes, remember, from the denominator. So if I take that, x squared minus x minus 2, set it equal to 0, we'll see that we can actually factor this into x minus 2 and x plus 1, which tells me that I have vertical asymptotes at x equals a +2 and a -1. Then we'll look to see if we have any horizontal asymptotes. Those are going to come from the ratio of the numerator and denominator, the degrees I should say. And because the degree of my numerator is less than the degree of my denominator, that tells me that we have a horizontal asymptote at y equals 0. And now I'm ready to set up my table. So to do that, we're going to start out with our test interval. So my test intervals are going to be from a -infinity to -1, -1 to 0, 0 to 2, and 2 to infinity. So then I'm going to come and pick some arbitrary x value that falls within those intervals. So here I'm going to pick a -2. Between -1 and 0, I'll do a -1/2. Between 0 and 2, I'll pick 1, and between 2 and infinity, I'll pick 3. I'm going to evaluate f of x. When x is equal to -2, I end up with a -1/2. When x equals a -0.5, I end up with 2/5 or 0.4. When x equals 1, I end up with a -1/2. And when x equals 3, I end up with 3/4. Then I'm going to look at the sign. And the sign is going to be negative, positive, negative, positive. And then I'm going to evaluate my points or find those. And I have a -2, -1/2, a -1/2, and 2/5. 1, -1/2, and 3 3/4. And now I'm ready to graph. So when we graph this, let's sketch our coordinate plane. And when we do this, we get the point -2. Let's do our asymptotes first. So my vertical asymptotes are at -1 and a +2. We know that we have a horizontal asymptote at y equals 0. And now I'm going to go ahead and pick my points. So I have -2, -1/2. So something down here. Then I have -1/2, 0.4 or 2/5. Then I have a +1, -1/2. And a +3, +3/4. Now, what's going to happen in our graph, and this is one that you're probably going to need a calculator to assist you with, is you'll see that we end up with something that looks like this. Kind of curves through the origin like this, and then is going to approach our asymptotes in these corners. So something that looks kind of like this here. And now for our last example for part 1, we have the function x squared minus 4 divided by x squared plus 4x plus 4. Immediately you should notice that you can actually factor this into x minus 2 times x plus 2. And we're going to divide that by x plus 2 times x plus 2. So our factors, or at least one factor in the denominator of the x plus 2's are going to cancel, and this is going to leave us with x minus 2 divided by x plus 2. We're going to continue to use the same process we've been using all along. Our y-intercept is equal to, it looks like a negative 4 divided by a positive 4, or we get y equals a negative 1. Our x-intercept is found from our numerator's zeros. And when I'm looking at my numerator, I'm really looking at this new function over here. So I end up with x minus 2 equal to 0, or x equals 2. Then I'm going to look at my vertical asymptotes, which come from the zeros on my denominator. And again, we're going to use these right here. So I have x plus 2 equals 0, or x equals a negative 2. My horizontal asymptote, I'm going to look at the ratio of my numerator and denominator, and I'm going to look at the exponent specifically. So I have a horizontal asymptote at y equals 1. And now I'm going to go ahead and set up my table. So for my table, I'm going to have test intervals, and my x-intercepts I have 2, my vertical asymptotes I have negative 2. So now let's fill in our test intervals from a negative infinity to a negative 2. Then we're going to look at from a negative 2 to 2, and then from 2 to a positive infinity. We're going to pick a test point for an x value, and I will go negative 3, 0, and 3. I'm going to evaluate f of x, and at negative 3 I end up with a y value of 5. At 0 I end up with a y value of negative 1, and at a value of 3 I end up with a y value of 1/5, or 0.2. Now I'm going to come into my table and look at the sign values. So I went from positive to negative and negative, and I have my points, which are going to be negative 3, 5, 0, negative 1, and 3 and 1/5. So now we're going to sketch this graph. So we have 5 up there, 3, negative 3, and negative 3. And now when I graph this, my vertical asymptotes, we said we're at x equals a negative 2. I also have a horizontal asymptote at y equals 1. So we're going to sketch that in. And now I'm going to plot my points. I have negative 3, 5, which is going to occur up here. Then I have 0, negative 1, and 3, 1/5. So now, if we use our calculator to kind of help us, you should get something that looks kind of like this and like this. And this is going to conclude our last example of part 1. Have a good night, and we'll see you tomorrow.